Hello and welcome back. Let us try to understand multiple linear regression with a bigger data set and with complete model building process, the data science model building process. So we have taken the same problem, the salary prediction, but a bigger data set, with more columns and around 1500 rows. Because the machine learning algorithm needs more data. And when you feed more data to train, it will understand better. It is like human beings only. If you have seen lots of world, you will have more information. If somebody asks a question, you will be able to answer it. Or if you have read more books, right, you will be able to answer more. That's kind of training happening to your brain. The same way, the machine learning algorithm also needs more data. So that's the reason why we have taken a bigger data set here. When we explained you the statistics and other concepts, right, we have taken small data sets so that the concepts are clear. The same data set, a magnified one. So let us try to do salary prediction. Again, the problem is the regression problem because the target variable we are trying to predict is a real number. So we have got this many columns in there, right? And those are called as input variables or independent variables or explanatory variables, and then the output variables, right? Target variable or whatever. The salary is the output variable. So in the initial stages of explaining multiple linear regression, we showed you on flowchart. The flowchart is like this. You pass the train set and the learning algorithm, here it is linear regression and we are passing multiple inputs. So we call it as multiple linear regression. And the algorithm, the hypothesis function actually learns the thetas, right? How much it should multiply each feature with to generate the value which is close to y. Once the model is good, you may pass your new record or batch of records and can predict it, the y cap. So this is what at a minute level or a 30,000 feet level we have showed you. But when you are trying to build a real model, there are other steps involved. So let us look at the process in a nutshell. So if you look at this, right, we take the data set from which has got x1 to xn features, n number of features and m number of records. And the first step we are going to do is split the data into train and test. We will explain you why we are splitting the data in the first step itself in a moment. Maybe by the time we end the the model building process with code example, we'll explain you. So we need to split the data. That's the first step. Generally, we take 80-20, 80% for training and 20% for testing, because always when you are training a human being or a machine learning algorithm, you need more data. When you feed more data, the understanding is going to be better. So we are taking 80-20. This is not enough. But if you have huge volume of data, maybe 10 million records, maybe you can take 10,000 records as test set and rest of the data for training, because you need more data for training, right? So in a small data set like these, right, we generally take 80-20 because decent amount of sampling should happen on the test set also while testing. Okay, so we use random sampling generally because random sampling most of the times works. We'll talk about stratified sampling in our classification example. So this is a regression example. So we are taking random sampling. Randomly we choose 80 records and take them as train set, and 20% of the records we'll keep them aside for the testing purpose. So unseen data, we are creating a situation where we production like data, right? In production, you will not be able to see data what is coming tomorrow or maybe in next moment. So we are trying to create that kind of a scenario by splitting the data at the first step itself. The second reason is that there is a concept called data snooping bias. If you pass the whole data, right, the whole m number of records through for training, and while before we train the model, you may do the statistical data analysis, exploratory data analysis. You may understand some pattern in this whole data, and you may choose an algorithm which is more appropriate to whole data, but it may not work in the production, right? So you have seen all the data, and with your intuition, you chose an algorithm. To avoid that bias, we split the data upfront. The third reason is that while doing the feature engineering, after doing the statistical data analysis, you may apply some techniques to clean up the data. So you need to test the cleanup code, right? The cleaning up code or cleansing code before you move the code into production. that can be done on the test set. So to avoid these three problems, we'll split the data, the first instance itself, and keep the test set aside. So we have got 80% data, and we took that as train set. And once after taking that train set, we'll do exploratory data analysis, a statistical data analysis, and do some feature engineering. As part of exploratory data analysis, we'll try to find whether there are nulls or not, whether the quality of the data is correct or not, kind of outliers. If you take one example, if it is the census data or the age of an employee is taken there, age should not be greater than 68, maybe 58, or the retirement age, right? So if there is some data which is 158 or something like that, we may have to correct it, or may have to remove it. So those kinds of quality issues we actually check. And sometimes we may have to merge columns and create a new column to improve the predictive power. Sometimes we may have to remove features which are not important. After doing statistical and business analysis, we may actually remove some columns. So to perform all these activities, we may have to understand data better. For that, we'll do statistical data analysis, and then whatever the activities we are doing, we call it as feature engineering. Sometimes we may choose features and all that stuff, right? So after doing that feature engineering, as part of feature engineering, we'll convert the categorical columns into numbers. That concept we'll learn a little bit in the code example now. If there are text features, right, even the text also need to be converted to numbers, because most of the machine learning algorithms understand numbers only. As part of exploratory data analysis and feature engineering, we'll do all these steps: imputing nulls, replacing nulls, or understanding quality and trying to correct, merging columns, removing columns, or adding new columns, or converting text or categorical columns to numbers. These are at a high level. We'll do more when we are working in real-time projects, on real-time projects. So once the data is ready, we'll feed it to AI or ML algorithm. It can be deep learning algorithm or a machine learning algorithm. We'll feed the data to algorithm. Once the algorithm is fed with the data, algorithm will learn the pattern. Here, it's a linear regression, so it will understand the coefficients of the features. From x1 to xn, there will be theta 1 to theta n coefficients will be assigned. We'll get a theta 0 also, that's called as intercept, right? X0 is always 1 for all the records, that's called as bias term. We'll talk about that more in coming classes. So once the algorithm learns the pattern, that's called as model. Once we have the equation, the proper equation to generalize the trained data, we call it as a model. Once the model is there, we'll pass all the x features, the input variables, x1 to xn only, no y. To learn pattern, we passed x and y both. Once the algorithm learned the pattern, we need to test it. To test it, we'll pass only the x's. Once we pass the x's, right, we will actually get the predicted values. The predicted values will be evaluated with error metrics. In regression, the error metrics are R-square score, root mean squared error. Right? Those are two examples. So once you calculate the error, evaluate the model, you will get some accuracy, right? If you look at R-square score, it should be always close to 1. If it is close to 1, the model is working good. If it is close to maybe 60 or 70, right, the model is not working good. Maybe the model is underfitted, right? If the model is underfitted, we'll do some fine tuning on the algorithm. Sometimes, when you do fine tuning, then also the model may not become better. In that case, right, we may have to go back and do exploratory data analysis and may have to do some more feature engineering. So we'll see that more in the coming classes. But here, we'll see a short circle here, right? After taking the train predictions, we'll evaluate, and if the model is underfitted means the model is not working well on the train set. That means the accuracy score is not coming good. Right? The R-square score is coming around 60-70%, right? So if it is the case, we need to fine tune the model. When the model is underfitted, we'll fine tune the model in gradient descent. When we use the linear regression, which is based out of gradient descent. So once the model is working good on train set, then we'll take the unseen data, the test set. Here also we'll pass only the x variables, because the model will predict the values for test set. We already have the values, the y values in the test set. we'll compare those two or evaluate the test set. And once the model is evaluated, if the model's accuracy is coming low, right? I said the model is working good on the train set. That means you are getting 90% accuracy on the train set. And when we passed the test set, you are getting 70% accuracy. That means the model is overfitted on the train set. Okay, this is called as a high variance problem also, right? So the model is overfitted, and then if the model is overfitted, right, we need to fine tune the model to work best on train set and test set both. What are we trying to do here? We are trying to generalize the model. Generalize the model where on seen data it should work well. The train set, the 80% of the data, the model should work well. At the same time, on the unseen data, the 20% of the data also it should work well. If it is working well on both the models, both the data sets, then we call it as generalized well. When the model is generalized well and working well on the unseen data also, then we can definitely use the model in production. So this is the whole process, and we will see this whole process with an example in the coming section. Thank you.